Hello, how are you? This um, lecturer, Dr. AMG. We are here to make little presentation on the continuity of functions. In our previous class already, we've considered that of limits. So today, we'll consider continuity of functions. As usual, the code that we have is MTH102, and in it, we're talking about calculus. But as I've earlier stated, the topic for today is continuity of functions. Continuity of functions. Now, as the word implies, continuity is about, in the ordinary sense, I would say continuity is about something that goes on and on without breaking, without truncation. Okay? Something that does not have abrupt change. Okay? Something that goes on and on. Now, in mathematics, you can say it's also similar. You can say it's also similar. Now, let's quickly give a brief definition of it. We are saying that a function, say f, is said to be continuous. It's said to be continuous at a point, say C, if and only if and only if f of x exists. If and only if f of x exists, and the limit of f of x, as x tends to c is equal to f of c, The function f is said to be continuous at a point, say C, if and only if f exists, f of x exists, and the limit of f of x is equal to this when you evaluate the function at that point C. Now, we are saying that for limits to exist, this simply means that the function must be continuous at the point C. We are saying that for the function to be continuous at the point C, the following conditions must follow. For the function f to be continuous at the point C, the following conditions must hold. The following conditions must hold. Now, one of it, the first one is f. Condition number one, f must be defined at x equals c, that is, f at C must exist. Then the second condition is the limits of f of x as x tends to C must also exist. And finally, we are saying that the limits of f of x as x tends to C must be equal to f after evaluating at the point C. Now, a function will be said to be continuous if these three conditions are satisfied. Now let's consider an example to see or to demonstrate what we have just said. Meaning that if it doesn't satisfy any of them, then we're saying that that function is not continuous. And if it's not continuous, then it's discontinuous. Now let's consider an example. So determine whether or not each of the given functions is continuous at the indicated points x equal to C. And number one, say A is f of x is equal to x minus 25 all over the square root of x minus 5, where C is equal to 25. Then say B is, say, g of x is equal to x plus 2 minus 3, where x is less than or equal to 5, and g of x is equal to this, where x is not equal to 1, x is not equal to 1, and minus 3, where x is equal to 1, for c equal to 1. Now let's consider these ones to illustrate what we have said. We are saying that a function f of s is said to be continuous if these conditions hold. Now let's consider this first. Now in testing for that, first condition is f must be defined at x is equal to c. Now in this one, c is equal to 25. So let's evaluate it. At c, we have 25 minus 25 all over square root of 25 minus 5. And this one gives you 0. This one also gives you 0. So we are saying that f of s is not defined. F of x is not defined at f You see, f of 25, where c is 25, is not defined. It's not defined, meaning that f of x is discontinuous at x equals 25. It's not defined. This criteria, this first criteria is not met. So we're saying that f of x is discontinuous at x equals 25. So if the function is not continuous, then we say it's discontinuous. For it to be continuous, these three conditions must be met. And we have seen that just the first one, it fails it. It's not defined. This is what we have. Now, let's consider this one. So there is no need for us to test these other ones. Now, let's go for this one. Let's go for this one. For this one, we have g of x, g of c, the first condition, g of c is equal to evaluating at c equals 1, meaning x is equal to 1, x is equal to c equals 1, which is this. So at c, then we are saying that it is g of 1 when x is equal to 1. And x is equal to 1 is this. And this we have as minus 3. So this one is defined. So let me put it here. X equals c is equal to g of 1 is equal to minus 3. G of 1 is equal to minus 3. When x is equal to 1, know that x is equal to c, and c is equal to 1. So, and it's that. Now, the first condition is, well, let's consider the second condition. The second condition is the limit of f of x as x tends to c, where c is equal to 1. So we are going to test it from both left and right. Okay? Now, when we consider the left-hand side, then we are saying that is this one. This one is when it's not equal to 1. So either the left-hand side of the limit, you will consider the neighborhood of this. So is this function that we will be looking at. So the function there is, what we have is x plus 1. Now, from the left, what happens? From the left, we are talking about 0.999999. 0.999. So if you put it here, is approximately 2, is tending to 2. And from the right, sorry, this is 2, this is 2, so it's tending to 3. And from the right, as x tends to 1 from the right, we have that f of x also tends to, from the right, we are going to have 1.0001, so which is also approximately 3, which is also approximately 3. So in this one, limit exists. Limit exists. Now, the third one is limit exists in this one. Now, the second condition, meaning the second condition is met. Now, the third condition is that the limits of the function, okay, as x tends to c, must be equal to f evaluated at the point c. X evaluated at the point c. And this we have to be 3 equal to this one will have to be minus 2. I mean minus 3. So they are not equal. It's clear that they are not equal. So this criteria was met. This one was also met. But this one, reaching this one, it fails. So we're saying that this one is not also continuous, but rather is discontinuous. But rather is discontinuous based on what we have. The first condition was met, the second condition was met, but the third condition fails. So we're saying that, first we are saying that g of x, first, g of x is discontinuous at x is equal to 1. So these are pretty simple examples that we have used to illustrate if the given functions are continuous at a given point. Remember, these are the conditions. We said f of x must be defined at the point x is equal to c. The second condition is that the limit of f that x tends to c must also exist. Whereas the third one is this one must also be equal to when x is evaluated at a given point. Now let's also give other examples to further explain what we are saying. Let's consider other examples to further explain what we are saying. Say example C, where we have h of c is equal to 1 all over 2 into x minus 3, where x is less than or equal to 5, and we have 1 for x greater than 5, where c is equal to 5. Now, let me also give one before I stop. Let's say this is p of x, where the function is 3x squared minus 5x plus 7, evaluated as c is equal to minus 1. Now let's consider this. This one already we just did a similar one, so the audience can also learn from it. However, we can still try it to further buttress or explain our points. Now let's consider C. Let's consider C. The first condition is f must be defined at x equal to c. So h of c is equal to h of, what is c? C is 5, equal to 5. Now, here we have x is equal to c, which is 5. So x is less than or equal to 5. So this is the function that we are using. So that's the function that we're using. So we have this one is equal to, evaluation at 0.5, we have 1 all over 2 minus 5, because x is equal to 5, minus 3. Now, if you simplify this, you're going to have 1 all over 2 into 2, and the end result is 1. When you evaluate at that point 5, the end result is 1. So f is defined at the point x is equal to c, x is equal to 5. Now we have to go for the second condition. The second condition says that the limit of f of s as x tends to c must also exist. Now let's see the limits of f of x as x tends to c from the left. Now what is c? c is equal to 5. c is equal to 5. Now the left hand side, when x is less than 5, so this is it. Now, what are the points that we are considering? The points that we are considering are when it's less than 5 are 4.999999. 4.999. So what we are looking at is we are looking at 1 to 2, 4.999, something like this, minus 3. So what is the answer that we are likely to have? The answer that we are likely to have is, you can see that this one is approaching 1 as well from the left. Now, let's consider the right-hand side limit f of x as x tends to c from the right. This one, we are saying that x tends to c from the right is x is greater than, because c is 5, so x will be greater than 5, and is equal to 1. And this one is equal to 1 because it's a constant function there. So you can now see that the limit as x tends to, the limit of f of x as x tends to c is equal to 1 from both left and right. So limits also don't exist. The limits exist. The limit exists. Now the next case that we want to consider is that of the last case, where we have the limits of f of x as x tends to this must be equal to this other case that we have defined. So we have the limit of f of x as x tends to c is equal to, must be equal to this, where this that we have is 1, where this that we have is 1, and which is also equal to this one that we have is also 1. So in this one, you can see that the three conditions have been met. So we can say that first, h of x is continuous at the point x is equal to c. Then we can say that first, h of x, the function h of x, is continuous at the point x is equal to 5. This one is continuous as the point x is equal to 5. Because this is the first condition, it was met, f was defined at the point x is equal to c. Then the second condition, we can see that limit also does exist. Whereas the third condition, the limit of that function is also equal, as x tends to c is also equal to the first case as we evaluated at the point equals c. So we say the function is continuous at that point. Now the other one is this last one, which is also pretty simple and straightaway. So next is this last one that maybe we can also just consider. This we can also consider. Now our interest is to determine if this function is continuous at that point. Now we are saying for the function to be continuous, these three conditions must be met. The function must be defined at the point x equal to c. then the limit of that function at x tends to c must also exist. Then finally, the limit of the function at x must also be equal to when it was defined. So now let's consider this. Now what we have, the first case now is P of C, which is equal to P of C is equal to -1. And this is equal to 3 into -1 squared minus 5 minus 1 plus 7. And if you deal with this, you're going to have 3 minus, plus 5 plus 7 is equal to 15. So when we evaluate at the point C, we can see that the end result is 15. It's 15. So F is defined. F is defined. Now let's consider the second case. The second case is taking the limit of the function. Saying the limit of the function as x tends to c from the left. As x tends to c from the left. Now c is -1. So from the left we are talking about -1.00000. So that's what we are considering. So we are saying that we are looking at where the f of x is, we are looking at 3 into -1.0001 all squared minus 5 into -1.0001 plus 7. And if you do this, the end result will be 15. It's approaching 15. It's approaching 15. Now, let's also consider the right-hand limit. The right-hand limit, let's also consider that. If we consider that, we're going to have the limit of the function, say f of x, as x tends to c from the right, will be equal to, that one is -1. So on the right, we have -0.999. So we have 3 into -0.9999 all squared minus 5 into -0.99999 plus 7. If you check this, you can see that this one is also approximately 15. If you check that, you see that the end result is also approximately 15. The end result is also approximately 15. Now, condition meaning that both from the left and from the right, we can see that all tends to 15. So we say limit exists. The limit exists in this case. Now, the last condition is this one, the limit, and when the point when we evaluated at point C, are they the same? Yes, if you look, this one and this one is the same. So we are saying that the limit of a function as x tends to c is equal to a point when we evaluated at c. Because we have for this one, 15 is equal to 15. So we are saying that the function p of x is continuous at the point x is equal to -1. So this one is also continuous. Now the next one that I will want to briefly talk about is that of continuity on an interval. Continuity on an interval. continuity on an interval. And let me also briefly give some definitions that will help us. Let me give some definitions that will help us. First, we are saying that if a function is continuous at each point of an open interval then it is said to be continuous on the interval. On the interval is said to be continuous on the interval. Then, two, let's take another definition. We're saying that the function f is said to be continuous. The function f is said to be continuous on the closed interval say a is less than equal to x less than equal to b. If f is continuous, at each point if f is continuous at each point on the open interval, which we have as this next to this, and also the limits the function as x tends to a on the right is equal to f at a, and the limit of f of x as x tends to b from the left is equal to f at b. Then lastly, the third one is f is said to be continuous on the half open interval say a is less than equal to x less than b, or a is less than x less than equal to b, if if it is continuous on the correspondence, if it's continuous on the corresponding open interval, A is less than X less than B, and the limit of f of x as x tends to A from the right is equal to f of A, or the limit of f of x as x tends to B from the left is equal to f of B respectively. So these are definitions that we have. We are saying that if a function is continuous at each point on an open interval, then it is said to be continuous on the interval. Two, we are saying that the function f is said to be continuous. It's said to be continuous on the closed interval, say a less than equal to x less than equal to b, if f is continuous at each point on the open interval this, where the limit of this and this is equal to this, and we are saying that the limit of f of x as this is also equal to this. Then finally, we are saying that f is said to be continuous on the half open interval this or this if it is continuous on the corresponding open interval this, where we have this expression. Now let's consider an example to demonstrate or illustrate that of continuity on an interval. Having taken this definition, let's consider an example. Example. Determine for which x the function f of x equal to square root of x squared minus 9 all over x plus 5 is continuous. Determine for which x the function f of x, the square root of x minus 9 all over x minus 5 is continuous. Now, solution. We are saying that let's consider this one, this part. We have to look at it in such a way that we don't have a case where we will have complex numbers as we have considered before. And this part also a case that we will not have values that will just a domain values that will not make the function undefined. So first of all, for this, we are saying that x must be less than equal to minus 3. X must be less than equal to minus 3. And x must be greater than or equal to 3. X must be greater than equal to 3. Now we are saying so because if x is less than this or equal, if x takes -3, -3 square will give you 9, and this will give you 0. So square root of 0 is 0. Now, being that is less than, the next term to consider is -4. If we consider -4, this place will be 16, and you see that we'll be having positive values. But if we consider bigger value, like -2, -2 coming here will make this one 4. 4 minus 9 will give us -5. And we'll have a complex number. So anything bigger than, greater than this, we don't need. And when it comes to the other part, we don't need -2, we don't need -1, we don't also need 0, we don't also need 1, we don't need 2, but 3 can also go. X, if 3 comes here, it will make this one 0. If it's greater than 3, 4, then it will also survive. So there are a range of values that we don't really want, whereas there are some that we want. But for this one holds. Now, the other one is this, where we say x plus 5. Now, if x takes -5, if x in this x plus 5, now if x takes -5, you will see that it will make this system undefined. If x takes -5, it will make the system undefined. So we don't also need -5. Even as we don't need -2, we don't need -1, we don't need 0, we don't need 1 and 2, we don't also need -5, because -5 will make the system undefined. Then what are we saying? We are saying that the function f has the domain, the function f plus the function f of x has the domain -infinity, comma, -5, union -5, comma, this one is inclusive, union, this one is inclusive, comma, positive infinity. Now, when you look at this, you will see that this one is not taking, that one is not taking, okay? So, that one is not taking, y -6, -7, all those ones are taking. Now, here, 4 is taking, -4 is taking, then -3 is also taking. Now, what we have omitted is just -5, -6 down is taking, then 4 and 3 is taking, then we're saying union 3, meaning -2 is not taking, -1 is not taking, 0 is not taking, 1 is not taking, 2 is not taking from this up. That is what we have defined here. So this one becomes the domain of this function. This becomes the domain, it's an interval, it becomes the domain of that function. Now let's begin to check, because our interest is to determine for which x the function, that function is continuous. And we are saying that it will be continuous if it satisfies the other the three conditions, where the first one, that f of x, f must be defined at x equal to c. Then the other one is the limit of f of x as x tends to c must also exist. Then we are saying that these two cases that we have made mention must also be equal. So now, first of all, let's consider the first case. Now, Let's consider this one. We have two cases for when x is equal to minus 3 and x is equal to 3. Now, at x is equal to 3, the function at c is equal to f is equal to the first one minus 3. And if you put minus 3 here into this function, it will make this place 0. 0 divided by this will also make this place 0. Now, the same thing here at x equals c, c will be f at 3 will also be equal to 0. Will also be equal to 0. Now, what do we do? What do you do? The next one that we need to check is the limits. So we are saying that the first case is defined. F of c is defined. Or you say the function f is defined at the point x is equal to c. Now the next one that we have to test is the second case, if limits also exist. Now for that of limits, we are saying that this one, x is less than, so this will be the left hand side, whereas we are saying that this one is we are saying that this one is x is greater than, so this one will be the right hand side. So for this function already we have said that this one must not be taken, because if it's taken to make the system undefined. So this one will serve for the left, whereas that one will serve for the right. Now for the left hand side limit, say the left hand side limit of the function as x tends to as x tends to negative 3. Negative 3. What are we looking at? What is f of x tending to? What is f of x tending to? We will see that f of x will also go to 0, because f of x here is this. So by the time you take negative this, so you are saying minus 3.001. So if you put it, it will be approximately 0. So that one 0 divided by will also make this one 0. So this one is also 0. Now what we are considering here, from the left hand side, the points are minus 3.0001. So if you square that, you will see that minus this 9 will give you approximately 0. So it will make this system 0. Now let's consider the right hand side of the limit. The right hand side of the limit as x tends to 3 from the right. As x tends to 3, this is what we are considering, as x tends to 3 from the right. Now, as x tends to 3 from the right, means we have 3.0001. If you put it here, it will also make this one 9.00001, which is approximately 0. And it will make the entire system also 0. It will make the entire system also 0. So for this case, therefore we can say is 0 for this case, and is also 0 for this case, based on these that we have. So we are saying that this one is also equal to this, and this one is also equal to this. So thus, the function f is continuous on that interval. Thus, we say the function f x is continuous on this interval. Is continuous on this interval. Now, briefly, before I stop, let me briefly talk about types of discontinuity. We are saying that if it's not continuous, then it's discontinuous. Now, for that of discontinuous, in the discontinuity case, we have types of discontinuity. One of them is essential discontinuity, which is the same thing as jump discontinuity, and we have another case where we have removable discontinuity. So let's briefly talk about types of discontinuity. Types of discontinuities. We have two types. One, we have essential, or you say jump discontinuity, and two, we have removable discontinuity. One is essential discontinuity, and the other one is removable discontinuity. Let me briefly explain with a diagram so that we can understand it better before we consider it algebraically or analytically. Let's consider this. Let's consider this function. Let's consider this function where we are interested in this. Let this correspond to this point here, 1, let here be 2, let here be 3. And here will be 1 minus 1 minus 2 minus 1 minus 2. And let here be, let this point be 5. Let that point be 5. Let here be 2. Here will be 4. Here will be 6. Here will be 8. Meaning here will be 7. Here will be 3. Here will be 1. Then 0. Now let's look at this function. Let's look at this function. Now you see that this function comes to this place, but this place is not taken. Whereas it starts from here, here is taken, then goes down. This one corresponds to this point here. This one also corresponds down to this point, 1. So this one, is it continuous? Now let's check. As x tends to 1, the limit, let's say the limit of f of x as x tends to 1 is what? You will now see that from the left hand side, it corresponds to this point. From the left hand side limit x tends to 1 from the left. That one is 5. It corresponds to 5. Now from the right hand side limit, it corresponds to 7. The right hand side limit, it corresponds to 7. So you can see that this one, limit doesn't exist. Limit doesn't exist. Now, for continuity, we can test evaluating the function at x equals 1. At x equals 1 is equal to 7. At x equals 1 is equal to 7. So f of x is f at c is defined, but then at this point is not continuous. That one limit doesn't exist. Therefore, we say that the first condition for that of continuity is not, is met, whereas the second condition is not met. So this type of, so this one is not continuous. Being that it's not continuous, we say is discontinuous, or you say is jump discontinuity, or you say is essential discontinuity, because you can also see it in this way. Now, look at the condition first. The evaluation at the point f of x at the point x equals c is defined, but then taking the limit, after we take the limit, you see that the limit doesn't exist. So a case where the first condition is met, but taking the limit doesn't exist, then we see that kind of discontinuity is called essential discontinuity. Say jump discontinuity. Now let's consider another example. For this one, the first condition, f at the point c is equal to 7 is defined, but the limit of f of x as x tends to c is not. Limit doesn't exist. Limit does not exist. So this kind of discontinuity we say is essential, or you say jump discontinuity. Now let's consider another one. Let's consider another one. Let's consider another one. If we have, say, we have this kind of function. So we have this kind of function. If we have this kind of function, where maybe here is, say, it corresponds here is 5. Say here is, say 0. Here is 2. Here is 4. Here is 6. Here is 8, and so on. Now look at this, and let's say here is 1. This one corresponds to 1. Here is 2. Now, the limit of this function, f of x, as x tends to 1, from the left, you see that it corresponds to this point and is equal to 5. And from the right, it also corresponds to this point and is equal to also 5. Both from the left is 5, and the limit of the function as x tends to 1 from the right is also equal to 5. Now, let's evaluate at x equals 1. At x equals 1 is not taken. Whereas in this one, at x equals 1, this point is not taken, but this point is taken. That was why at x equals c, we have 7. Whereas in this case here, now based on what we have here, at x equals 1, when we evaluate f of c, where this is equal to 1, is not taken. It's not defined. It's not defined. Okay? Yes, limit exists. Limit exists. Both from left and right, it tends to 5. But at that point where f is where we determine the value of x at the point c, is not defined. Then we say this kind of discontinuity is called removable discontinuity. For it to be continuous, we have said f must be defined at the point x is equal to c, and we have said that the limit of f of x as x tends to c must also exist. And finally, the two cases that we have been mentioned must also be equal. But in this one, you can see that the first point, the first one, the first criteria, it didn't meet the first condition. So we are saying that it's not continuous. And if it's not continuous, it's discontinuous. By what kind of discontinuity? This one is called removable discontinuity. Removable discontinuity when f at c is not defined, but the limits of f of x as x tends to c is defined. Then that kind of discontinuity is called removable discontinuity. Now let me give just small example, few examples to also help us understand what we are talking about. Say example. In each of the following, classify the given point C as one of continuity, essential continuity, or removable. Essential, discontinuity, and removable discontinuity. And the functions that we have, one is f of x is equal to x squared minus 6x plus 5 all over x squared minus 4x plus 3, all where c is equal to 1. And 2, we have, say, g of x is equal to x plus 3, x squared plus 1, where x is less than 3, and x is greater than equal to 3, where c is equal to 3. Now in this one, let's try to see if it's continuous, and if it's not continuous, then what kind of a discontinuity is it? Is it essential discontinuity or removable discontinuity? Let's just briefly check before we call it a day. It will be continuous if the three conditions are met. F must be defined at x equals c. It will be continuous if the limit of f of x as x tends to c must also exist, and both f at c and the limit must also be equal. Then if it's not continuous, then we say that it's discontinuous. Then what type of discontinuity? Is it essential discontinuity? It will be essential discontinuity if f at c exists, but the limit, if f at c exists, but the limit of f as x tends to c does not exist, then it will be removable discontinuity if f at c does not exist, but the limit of f as x tends to c exists. So let's test in one of the cases to see which type of, either it's continuous or discontinuous. And if it's discontinuous, then what type of discontinuity, essential or removable discontinuity? And let's use this one to illustrate. Now, first of all, is it continuous? It will be continuous if we evaluate at this point x equals c, where c is equals to 1. So if we put 1 here, 1 here, 1 here, so this and this will give you 6, and this one will be 6. So that one will be 0, and this part will be 0. So at f of c, we have f of 1, which is equal to 0 in this case. Is equal to 0. So you can see that the function f as x equals c is not defined. It's not defined. So being that it's not defined, then means it's not continuous. Then if it's not continuous, what type of discontinuity is it? Is it essential or removable discontinuity? Now let's also check. Let's take the limits. If we take the limits of this, you will see that this side is also, this one will also be 0. If we take the limit, no, it will not be 0 because it can be simplified. Let's look at it. F of x is equal to x squared minus 6x plus 5 all over x squared minus 4x plus 3. This we can also write, this we can also write as x minus 1 into x minus 5 all over x minus 1 into x minus 3. Where this and this is off, and you will be left with this. So when we take the limit of that function, where the function is x minus 5 all over x minus 3, as x tends to 1, as x tends to 1, will be, this one will be approaching this, and this other part will be approaching 2, and the end result is 2. And the end result is 2, both from the left and from the right. Both from the left and from the right.